If you split pure white light using a prism, you will see a smooth, continuous rainbow. But if you do the same with sunlight, the result is slightly different. Instead of a perfectly smooth spectrum, there are thin dark gaps, specific colors missing. What causes those gaps, and how can they tell us something about the sun? To answer that, we need to understand the different types of spectra. A continuous spectrum contains all the wavelengths across a range, arranged smoothly from longer wavelengths to shorter ones. Light from hot, dense sources, such as incandescent bulbs, or the dense interior of stars, produce a continuous spectrum because many wavelengths are emitted at the same time. However, not all light sources behave this way. When light is governed with individual atoms in a low-density gas, the spectrum is no longer continuous. Instead, only specific wavelengths appear. This produces a discontinuous spectrum, where some colors are present and others are missing. One way this can occur is when atoms release light directly. In this case, the spectrum appears as bright colored lines against a dark background. This pattern is called an emission spectrum. Each element produces a unique pattern of emission lines. No two elements have the exact same set of lines, which means these patterns act like fingerprints. By matching the pattern, scientists can identify which elements are present in a light source. There is another important type of pattern formed when light interacts with matter. If a continuous spectrum passes through a cooler, low-density gas, the result looks different. Instead of bright lines on a dark background, we see a smooth rainbow interrupted by dark lines at specific locations. This pattern is called an absorption spectrum. An absorption spectrum forms because atoms in the gas absorb only very specific wavelengths of light. They do not absorb all colors, only certain ones. The absorbed wavelengths correspond exactly to the same wavelengths that the atoms would emit if they were energized. As a result, dark lines appear in the same positions where bright emission lines would normally be seen. In other words, emission spectra show which wavelengths atoms give off, while absorption spectra show which wavelengths atoms take in. By studying these patterns, scientists can determine both what a light source is made of and what materials the light passes through on its way to us, even when that source is extremely far away. If you want to discover why those exact lines exist, exploring the hydrogen spectrum is the next logical step. Thanks for joining me on MN Horizons.